Okay, thank you everyone for joining us today. We're going to go ahead and get started, and I'm going to have introduce Dr. Jacob Rindler to get the webinar started. And I just wanted to let everyone know we will be doing a Q&A at the end. You will see a little box at the bottom of your screen that says Q&A. You can submit any questions you have in there throughout the webinar, and at the very end, we will go ahead and answer them. So with that being said, we'll go ahead and get started.
All right. Well, hi there, everyone. Thanks for joining. My name is Jacob Rindler, and today you're part of the webinar series put on by ADDMAN, and the topic is Better Than Wrought: How Optimized AM Material Properties Are Enabling Hypersonic and Spaceflight. And what I want you to take away from today is that the right material choices are not about kind of meeting the thresholds of set by traditional methods, but rather really when you pick the right materials for additive manufacturing, you should get a optimized set of material properties that can maybe exceed what you can achieve with traditional manufacturing methods. So again, my name is Jacob Rindler. I'm the Director of Materials and Manufacturing Technology at ADDMAN, and predominantly support our metal additive manufacturing group, Castion. So with that, we'll get started. So real quick, we'll do a company overview so you can find out, if you don't already know who ADDMAN is and the companies that make up the ADDMAN group and sort of what they do as well. So, but most importantly, like behind that is our vision and mission, which is, really to power a better tomorrow using additive solutions. And what we really like to say is we're a manufacturing solutions provider that's enabled by additive manufacturing. And that means a lot of things, really, all the way up front with engineering and R&D services when ideas and challenges are really just starting to be formed, all the way through being your trusted manufacturing partner through the prototype and full-on production life cycle of a program. With our metal and polymer additive manufacturing business, and also sort of our more established, maybe even higher throughput manufacturing divisions focused on CNC subtractive manufacturing and also plastic injection molding. So where are we at? So we really stretch from coast to coast. So starting from Baltimore or Glen Burnie, Maryland, we have a machining production center there that has multiple CNC machines, does very high throughput, a lot of aluminum machining. Our location in Rochester, New York, which is home of all of our polymer injection molding. They also have a full mold making tool and die mold making shop there, as well supporting precision machining of complex components, as well as we even do some manufacturing of things like metal coils for solenoid production. We recently, or the newest add to the team, is our metal additive manufacturing production center that was formerly Keselowski Additive Manufacturing. That's in Statesville or the Charlotte area. Very excited to have them join the team. Great team, and excited to unlock the future together. We have our corporate headquarters, which opened just over a year, or a little over a year ago, in Fort Myers, Florida, which has some of our R&D as well as corporate functions. And then we have a location in Wright City, Missouri, that does, precision machine of really large, complex aerostructures, especially from hard metals like titanium. We also have a location in Rochester, Minnesota, well known for supporting the national security mission, Honeywell FMT, as well as doing a lot of different exotic materials, as well as some friction stir welding assembly for cold plates. And then finally on the West Coast, we have Castillon and Dinsmore. So Castillon being our metal additive manufacturing and hypersonics focused development center, as well as doing a lot of our serial production for refractory materials. And then also down in Irvine, we have our polymer 3D printing specialist at Dinsmore there. So again, coast to coast, over 350,000 square feet of footprint with room to keep growing, as well as over 650 employees, many of them being engineers. And so we can really take, again, work with you up front on developing the requirements and the engineering to manufacture something through the life of a program, and then also go ahead and execute on that. With a range of certifications ranging from ITAR, AS9100, all the way through things like ISO 14001 and 13485 as well, with others coming. So looking at our metal AM capabilities, we're a machine agnostic metal additive manufacturing company. So really we have a number of different platforms. Some of them do things really well, and some of them specialized on more so production, large scale production machines, highly productive with many lasers, all the way through smaller, really R&D focused machines as well. And kind of everything in between. And we really have done that strategically as sort of supporting the technology development, especially in laser powder bed fusion, of really working with many OEMs to push the boundaries of what's possible. And of course, going into the heart of today's discussion is all the materials that we print. So you'll see many on this list that are familiar, and some maybe that are a little bit less familiar, and we'll talk about why maybe some of them have more benefits to those who want to make metal additively manufactured parts. And sometimes we say that the printing is the easy part, and really it's the post-processing. And so that is sometimes the challenging part of the additive production process. And so we're very lucky to have experts for CNC machining across the company, across the coast, both coasts and everywhere in the middle, to be able to have so much capacity to CNC machine, post-process machine our metal additive manufactured parts. So you can see there over 100 machining centers across the company. And so what do we do? How does that impact the industry? So you can see some of the cool stuff that we're able to share. Everything ranging from products on the stealth products on the F-35 that are consumables such as those LO panels that help keep that system stealthy, all the way through our serial production additive parts that are space thrusters for rapid propulsion, chemical propulsion in space, made from C103. And then you can see there on the right-hand side, large aerospace structures, and all the way through complex machining of those. So whether we're adding inserts and bolts and fasteners, or more complex mechanical assembly with systems, and you're seeing down there basically a splice cutter for a aerospace platform that is a pretty complex piece of assembled hardware. And in the bottom left, one of the things that we'll be talking about is refractory, printed refractory materials, and see some representative components there, ranging from power generation all the way through, again, space propulsion and our hypersonic products as well. So survivable, scalable, affordable TPS systems for the front end of these hypervelocity applications, all enabled by especially in the metal additive manufacturing arena, enabled by advanced material choices. So getting into the meat of our presentation or the webinar today, and hopefully discussion, we'll have questions after this. But with raw materials, the majority, or with additive materials, really kind of where we started is using more traditional materials that are widely available to be atomized, and are wide, obviously have a large user base within the especially aerospace community. But those materials were designed for specific manufacturing processes. Oftentimes they were the ones that are most successful are ones that have really good properties in their wrought form or plate form, even cast form, but then also can be welded because if you can't if you can make something but you can't assemble it into the final shape or repair it, that often creates some challenges as well. So we've kind of seen this maybe group of 5, 6 alloys, nickel 718, 625, grade 5 titanium, so Ti6Al4V, aluminum 10 silicon magnesium, maybe 316L stainless steel that sort of have this huge presence in the market. But not saying they're great, they're not great alloys, but if we really want to talk about getting the most performance out of our additive manufactured process, we can start making some more judicious material choices that really suit the manufacturing process to the strengthening mechanisms that we're hoping to achieve to get the most optimized set of material properties, which is really kind of needed for these, uh, ultra, high temperature applications, especially in hypersonics, where we're seeing, the systems, the design of the systems themselves is now limited by the materials that we have available in our toolbox. So hopefully what you'll get away from today's discussion is a view on, or at least how we at Castion and ADDMAN view that if you pick the right materials with the right manufacturing process, it's not about achieving this set of wrought properties, that have been historically there, but really, potentially exceeding those. So yeah, let's get into the meat of it. So when we look at sort of Castion and now ADDMAN's approach to metal additive manufacturing is really material centric, and but maybe not in the same way that you might see in maybe some papers or case studies out there. How we really kind of differentiate ourselves in this material centric approach is when you look at a manufacturing challenge, going back to, hey, what are the material properties that are the most important for that application? And then, from there, you start to understand, okay, what sort of strengthening mechanisms and other sort of intrinsic properties are this material going to need? And from there, you can back out really what is the right chemistry? What should this material have in it from a primary elemental component, and really looking at it from if we're talking about a specification, what is the right range to get the right microstructure and strengthening mechanism we want out of this alloy? And so our founder, Yuping Gao, developed the Gao block as sort of this process and material, not only quality control artifact, but also development artifact. And you can see that there in the bottom left hand of the screen. The Gao block, you see this out there in industry almost is quite common as not only a quality artifact, but again sort of that development artifact as well. And we continue to use this on all of our build plates that we print at Castion and ADDMAN. And so once we have the chemistry that we think is going to develop, or is going to result in the right microstructure and properties that we want, then it's really about on a weld by weld basis, we're looking to get the right microstructure formation, and that's related to the cooling rate. So that's the aspect of the weld pool of the processing parameters that we're getting the right sort of ratio of velocity, which is going to control the solidification as well as the temperature gradients, along with the power itself of the laser. And that's what we're looking to get the right microstructure, and maybe secondary phase formation as well. And then finally, where oftentimes you'll see sort of these process maps of the first thing being developed is sort of a laser speed versus power sort of curve, where we're looking for optimizing density. That's really the last thing that we really optimize for, because at that point, really, it's a geometric problem. But if you want to get the best material properties, you got to start with the best microstructure that you can get from the manufacturing process. And then also keep in mind some of these alloys are heat treatable, and so we also you have to have an understanding of that, and some of the alloys that we work with work really well with sort of just a stress relief only heat treatment, and others ones we do sort of age hardening type heat treatments as well. So that's really when we talk about getting or beating Wrought properties, we kind of have this standard sort of playbook or way we view the problem that we bring to a diverse set of manufacturing challenges. And sometimes it's high temperature performance, and sometimes it's creep performance, and sometimes it's special properties like magnetism. So it kind of varies. But we kind of come back to the same type of approach. So now let's get into some specific use cases here. So you'll see here advancing superalloy manufacturing. Inconel 718, Inconel 625. Huge levels of adoption in the additive manufacturing world. I would say my guess is probably there's more Inconel 718 printed than any other alloy. Definitely any other nickel super-based alloy. But there are certain applications where it makes a lot of sense. The economies of scale it makes it for very affordable pricing for the powder and wide amounts of availability. But when we start looking at high temperature applications, because Inconel 718 is a gamma double prime strengthened alloy, it's susceptible to basically kind of this cliff as where the properties fall off as a function of increasing temperature, because those strengthening phases are going to dissolve back into solution at say like around 1800 degrees Fahrenheit. Same thing for Inconel 625 is not precipitation strengthened, but it's solid solution strengthened. But it's going to have some issues, especially around lavase phase formation, and there's a lot of molybdenum in there that isn't as necessarily effective as a solid solution strength at higher temperatures. And really where these alloys have seen their a bunch of use really is around because they were well suited to having solidification temperature ranges that are suitable to allow them to be gas tungsten arc weldable. Didn't really have the weldability challenges of maybe some higher strength alloys, such as like MARM 247, or some of like the wasp alloys, where you kind of run into weldability issues and reheat cracking issues from gamma prime formation, things like that. And so when we had our customers had were looking for nickel superalloys that had better performance, really is driven by the hypersonics and the launch community. And so when we looked at Haynes 230, there's a lot to like there. One, from an ease of post processing, it is solid solution strengthened, and then from high temperature performance, because it's primarily strengthened by tungsten carbides. Tungsten carbides are inherently very thermally stable, and what the challenge of maybe the material from a weldability standpoint was really able to be addressed by picking, when we talk about using the right chemistry, picking the right band of chemistry to get a alloy in the right processing window to get an alloy that doesn't have weldability issues. But when we look at the microstructure now, of the printed material over the wrought material, this is one of those instances where, if you look in the materials handbook and you say, hey, what is the material properties of Haynes 230 and the regular wrought microstructure, you kind of see, just one story. But with additive manufacturing, in laser powder bed fusion especially, we've really been able to reinvent this alloy because we pick the right chemistry, we get the right strengthening mechanism. So what you're seeing here is we compare between the right and the left, the right being the raw and the left being the additive manufactured material, is we're able to get these tungsten carbides forming coherently within grains at very fine length scales, but also along the grain boundaries. But we have really refined grain boundaries as is typical of a rapid solidification process. And so how that manifests itself in material properties, I'll show you here on the next slide. But here in 2 slides. Here, I wanted to go talk a little bit more about the microstructure. So if you look in literature, some folks have worked on Haynes 230, and it can, from a robustness standpoint, it can have hot cracking issues and microfissuring, which of course would degrade your properties quite a bit and is unacceptable. But when you pick the right chemistry, you actually are able to mitigate these issues in the right material properties, as you can see here on the right-hand side. Looking at in the middle there, you can see the Haynes 230, sort of this, nice 3-dimensional representation of the microstructure and the various orientations. And you can see these large tungsten carbides forming at the grain boundaries, which is going to limit your suitability at high temperatures over the length as it's, especially in creep performance as it's subjected to constant load. And so really what we're looking for here is this dense as well as optimized microstructure that with the tungsten carbides forming after just a short heat treatment, again, coherently within the grains. And you kind of see over here the difference in chemistry. So whereas ENL 625, a lot of molybdenum in there, and molybdenum is going to form these carbides, these strengthening carbides as well as be a solid solution strengthener. But we can see here that we have about 14 weight% tungsten. That's going to act as a solid solution strengthener. And then also form those carbides. So when we look at the material properties themselves, and you can kind of see here on the left-hand side is the spec required minimum for Haynes 230, as well as the typical values. And we can kind of see here the ultimate tensile strength, yield strength, percent elongation. So, highly ductile alloy has pretty good strength in its wrought form. Been used a lot for combustor type applications in the turbine engine community for years. But when we go to the as built or additive manufactured version, we can see here the AM as built, the AM stress relieved, and the AM hipped. All across the board, we're able to still retain most of our ductility while getting much higher yield strengths as well as ultimate tensile strength. And why we see a little bit of degradation property from the stress relief, we know we get a little bit of relaxation of residual stresses, which can and these were taken in the Z direction, which can reduce your yield strength a little bit, but also the ultimate tensile strength slightly increases because we are getting a higher fraction of those tungsten carbides precipitating out. And then during the hipping process, at the high temperature plus combination of high pressure is something that causes it to start to recrystallize, and so we get a little bit of that. The benefit of having that reduced grain size starts to go away, and so we see a slight degradation properties, but a slight uptick in elongation. But what has us really excited about this is we retain those benefits in our strength as well as elongation all the way out to 1800 degrees Fahrenheit out here. You can see the comparison between the wrought and additive manufactured version at 1400 here and 1800 there on the far right hand side. Again, still remaining highly ductile, but we're getting these increases in strength over the wrought alloy. So if you were to look in, say, the like the material handbook or like MMPDS as a designer, and check, oh well, hey, if I just look for wrought properties, yeah, maybe this alloy would want me to, I would want to pick something else. But when we look at the this is where we got to do these investigations and pick the right material and process combination to solve those kind of difficult manufacturing design challenges for these kind of next generation systems. And so what I've plotted across here too, just for everybody's reference, is where the stars are is that data that is in the open source for additively manufactured Inconel 625. And so you can see, when we look at it in comparison, there are clear benefits to, it's saying like taking an Inconel 625 application and pursuing Haynes 230, because at the end of the day, higher strengths at temperatures, means ultimately lighter parts. You can see here on the right-hand side, some potential applications of Haynes 230 that you can have in the launch community. So switching gears a little bit, so we've been talking about some of the benefits for nickel-based superalloys and picking the right alloy. The same can be said for refractory alloys. So niobium C103 is the most common aerospace niobium-based alloy. Very has a long flight pedigree. Even going back to the Apollo lunar lander. And this is another material where because of the unique microstructure and secondary phase formation from the laser powder bed fusion process, we see some real clear benefits for the printing of this alloy. And so you can see here on the left-hand side, kind of the traditional wrought and annealed structure. So, kind of typical, cellular type grains formology, morphology, and then when we look at the printed version, we can kind of see very clearly in the as printed as well as annealed that we still retain all of this weld macrostructure, which we'll get into why that's important here in a little bit. But you can see clearly, we kind of have that a little bit of propensity for grain growth across the layers. And you can see, clearly the weld tracks here. So we're talking about weld pools that's 175, 225 micron-ish wide, and about the same in depth. And if you're not as familiar with niobium C103, you can kind of see the alloy composition here. So about 10% hafnium and 1% titanium. And whereas the nickel super base alloys, we're talking about melting temperatures of the 3000. We're talking melting temperatures for niobium based alloys in the 4000 degree plus type Fahrenheit, while also still having a density that's pretty similar to those of other nickel-based super alloys. So not a huge weight debit from something like this. So getting into why this material benefits from the additive manufacturing process, and why we can actually beat the wrought form of this material. It really comes down to the printing process. And you see here, we'll talk first about the microstructure. So, again, laser powder bed fusion, we're talking, over 1 kilometer a second of laser travel speed, and, temperature gradients that can be, or cooling rate here that can be in like the 10,000 degree per second realm. And so we get a microstructure that is going to be very refined, resulting from that rapid solidification. And then we also get formation of these very fine secondary phases, such as hafnium carbides and hafnium oxides, at very fine length scales. We're talking, tens, hundreds of nanometers, both at the grain boundaries, as well as you can see here in the lower left-hand corner in this SEM image, dispersed throughout the grains, and the grains themselves are in the order of tens of microns in size and in either orientation. And so we get a refined microstructure, so we're going to get hull pet strengthening as well as sort of this dispersoid strengthening effect that we wouldn't typically expect to see in the wrought counterpart. And so why is that important? Why do we see higher temperature strength and better creep performance? So that really comes down to those secondary phases. And so you can see here, when we look at the as printed material versus the bar stock material, you kind of see the difference in kind of, you have this weld macrostructure view. The grains are too refined to really clearly pick out in at this magnification, versus we can kind of see individual grains here in this view. And then if we expose this material at 2,900 degrees, so almost 3,000 degrees Fahrenheit for 2 hours, we can see the difference this effect of this has on the different types of material. So in the AM version, we can still see that retained weld macrostructure that we get from the process. And so this material is going to be very thermally stable and is going to have better properties and properties that don't degrade at higher temperatures through the service life of the material of the component, versus the raw material. We can see sort of explosive grain growth, and that's going to let you know that, hey, we're going now get the strength benefits of having a refined microstructure is going to go down, and then the material properties are going to be changing as we sort of get this constant growth and elimination of grains in sort of the raw material. And that's really related back to those hafnium carbides and oxides forming at very fine length scales during the printing process itself. And so you can see when we talk about strength, and all the way at 2,000 and 2,400 degrees F, out of 2,400 degrees F Fahrenheit, we're seeing a almost double in the ultimate tensile strength, and even improvements in the yield strength, while still retaining ductility, which tells us, hey, this is a really good candidate material for that's going to outperform its wrought counterpart, and we've demonstrated that now. And we have many customers now designing off of these new additive manufactured properties that we're developing together in collaboration, rather than going back to the traditional wrought material values that they might find in, say, like a on like a data sheet for this material dating back 30, 40 years. And it's not just tensile strength or elevated temperature tensile strength. There's other properties that benefit from the laser powder bed fusion process as well. So first we'll talk, kind of show maybe a little bit more comparison at a suite of temperatures here. So, and talk a little bit about some other alloys too, that in the niobium-based system that benefit from the additive manufactured process too. So, going from the top to bottom on the key here, we have the blue diamonds are the wrought material. Tested in vacuum, so the ultimate tensile strength and yield strength, and then also the AM C103 material that were also tested in vacuum, so those are the red diamonds. We have some AM material in the red squares that was tested in atmosphere, but was coated. And then another alloy, which is WC3009, which is another niobium-based alloy that has upwards of 30% hafnium in it. That you can see here of where it gets charted out of a even higher strength alloy that is very printable, and then a material that we're just starting to develop or putting or really getting put into use is our Castillon Super C103 material with more data forthcoming. So you can see, kind of across the board, even the material tested in air which is traditionally, this material oxidizes readily and rapidly degrades at high temperatures and in atmospheric environments. You can see even at that temperature, high temperature, it's beating the traditional wrought material when tested in air. And tested in vacuum, we're seeing, much higher performance, kind of as we showed in the last slide. And then WC 3009 with the added hafnium content, we kind of see that it's a higher performance alloy even at much higher temperatures. But what's important out here is even with some of our applications going up to 3000 degrees F, we're still seeing measurable benefits to the additively manufactured material, which is really exciting. So I talked about not just ultimate or elevated temperature tensile strength, but also creep performance. So you can see here the comparison between the wrought material tested at 800 degrees Fahrenheit in an argon environment. The raw material was annealed, as was the AM material at 2600 degrees Fahrenheit. And you see whereas this specimen failed at about 2% creep after 15 hours, we saw no measurable creep at 15 hours or even out to 25 hours. And so we, while increasing the load on the creep frame itself, and you can see the material, the AM material, didn't fail until almost out of 14% creep with almost double the load. And so, that's really exciting for some of these long life type components. We talk about reusable hypersonic vehicles someday. Their TPS systems, aren't. If we go to like an ablative system, we'll never get the reusability that we want. And so this is really exciting to see these materials not only be able to survive, say, in a single-use type application, but also, this gives us high confidence that in a reusable type application, this material could also really perform quite well too. So diving deeper into the microstructure and the grain morphology itself, you can kind of see, I talked about the cellular type grain structure, pretty planar type grain boundaries versus the laser powder bed fusion process. We kind of see this really tortuous type grain boundaries forming, really refined grain structure. And this is going to have benefits when we start talking about the oxidation resistance. So if we look at the, one of the downfalls or one of the challenges of refractories, especially niobium-based alloys, is they readily oxidize. And it just so happens that the niobium pentoxide that can form has a melting temperature quite a bit less than the base material itself, all the way down here at 27 degrees F, 2700 Fahrenheit, when many of our applications are potentially at 3000 degrees F or more. And so when we look at the grain boundaries and why we're seeing a better oxidation resistance, I kind of equate it to a racetrack. So when we look at like a drag strip with these straight planar grain boundaries, because oxidation is a diffusion type mechanism, the oxygen from the atmosphere or the surrounding the material is able to penetrate along these grain boundaries at really high rates, forming these pentoxides and liquating and degrading the strength of material quite readily. When we look at the AM material, and we have these sort of tortuous, grain boundaries that doesn't allow the oxygen to penetrate. And then we also sort of get a mechanical interlocking effect of the grains themselves. We're able to see that we have better oxidation resistance. And this was actually material that was tested in a oxidized environment of basically the propulsion stream of an actual tested engine. and we dissected, or we cut up the material and analyzed it after the fact to better understand why the AM material is more oxidation resistance. So that, combined with robust coating technology, now we have a substrate that's more oxidation resistance, and coating technologies that has been proven to work as well. And so we have some pretty good options there to have this material operate in pretty strict extreme environments. So talked about the materials. So why does that matter, I think, is what I would like to share as well. So when we talk about in the hypersonics, I mentioned before that these materials, or these systems, I should say, are material limited today. The performance, or the design window of them, is dictated directly by the materials in which we can manufacture them. And so refractory metals and some of these materials that we've transitioned from R&D to developing them into highly productive and sort of robust manufacturing processes have some real benefits over maybe some of the other materials that could be used. So for instance, if we look at comparison for a aero shell made of refractory metal compared to say like carbon-carbon composite, we estimate that we can save around 50% of the cost. And if we start talking about needing to continually change out the TPS, say for like a ablative tile TPS system on a reusable, we could be anywhere around 200-300%, maybe even up to 500% savings for a reusable system, because we now have a TPS that will potentially survive the life of the vehicle itself, and extremely high temperature performance. So we've proven this material not only in flight applications where we're in serial production today, but also in things like hypersonic test tunnels, such as the Arnold Engineering Development Center, Tunnel 9, where we've gone on tens, dozens, maybe even potentially hundreds now, Mach 18 type tests with our components, where they replaced out the wrought material for the additive manufactured material. In addition to that, we have a non-ablative material. So when we start talking about the control system and the aerodynamic performance, we don't have to model in the changing of the geometry, and then also because it's shape stable and it's highly conductive, maybe we don't need to use all the energy or the maneuvering power of a vehicle to mitigate heating concerns. And then also because it's a metallic material, it's inherently more in, say, like impact resistant than maybe a more brittle material, and then also can withstand concussive shocks better, and then also it's scalable. So we've proven with manufacturing readiness assessments that we don't have any hurdles to implement this for a vehicle with say like a target rate of 10 dozens a month. And so you can see here sort of some of those systems, and then also are some materials that are what we can share, some manufacturing demonstration articles here. So, and why refractories, why hypersonic systems? So, I think that this chart really illustrates that well, as we look at the performance, the increasing performance of nickel super-based alloys as a function of year. We've kind of leveled out the performance gains as a function of time we've spent investigating these nickel-based super alloys, and we can see that the refractory alloys are really that's kind of step change. And additive manufacturing offers us an opportunity to overcome a lot of the early sort of manufacturing challenges that those refractory alloys sort of face in their implementation. And so now the combination of the printing process plus these high temperature chemistries where we're seeing these market improvements in properties over the raw material is really enabling things like the propulsion industry as well as the hypersonic structures community. So it's not just done in the lab either. So you can see here, it's not often that we get to share too much, but these are some demonstration components that are out there in the public space. We've printed extremely complicated turbine blades, showing that we could implement this into a power gen type application. Numerous hot fire testing proving that this material is better. The laser powder bed fusion niobium C103 that Castheon prints is better than its Wrought counterparts, and all the way through printing special structures that can even help improve the high temperature performance even more so, not just from a material perspective, but also from a design perspective. And of course, long history with C103 in the space propulsion arena. And these are just some demonstration components. But what we can say openly here is that this has flight heritage. It is proven. We are in serial production with these type of applications today, and happy to partner with you on your manufacturing challenges. So, closing thoughts. Thank you for spending the time with me today and the interest. I'm a welding metallurgist by heart, so I'm really excited because the future is bright, not only just for additive manufacturing, but also the blossoming of new materials that are going to be made available here in the coming years. The space and hypersonic industry are definitely leading adopters because they have to be, because we're now maxing out again what materials can do, and so we have to naturally open up that toolbox of materials available. And Castheon is here to help. We want to be your partner from a not only an R&D perspective, but also from the ADDMAN group perspective. We want to be your partner through the life cycle of development through serial production. So with that, I'll go ahead and stop here, and I'm sure Hope will be getting everybody ready for any questions you have. So my information's there. We're growing, we're hiring, so please check out the ADDMAN group career page. And then also, a lot of this work was done with some really fantastic partners, not only from a customer perspective, but also a development perspective. So NASA, Marshall Space Flight Center, ATI, the Air Force, Air Force Research Laboratory, Air Force Tunnel 9, Amero, as well as many others. So thanks, and looking forward to chatting about your manufacturing challenges soon.
Okay, we are going to move to the Q&A portion of the webinar. So I will pass it over to Jacob. And if there are any questions we don't get to before we run out of time, we will follow up with you.
Thanks, Hope, and thanks everybody for joining today. Really appreciate your time and attention. And we do have a couple of questions here. So I'll start first with a question from Lawrence Russell. Are heat requirements for satellite and space launch rockets getting higher? What emerging demands does this higher heat resistance alloy serve? So when we think about what does the higher performance get you, not only does it increase the temperature window, so higher temperatures, but also when we start talking about specifically for propulsion applications, the duration or the duty cycle of that the engine can serve is a major one, especially in terms of oxidation resistance. That has many benefits there, and then also when we start talking about maybe redesigning of traditional components, able to remove weight from existing designs because we have a material that's slightly stronger at maybe the same temperature band. So I would say that's kind of where we're seeing the added benefits of additive manufacturing being utilized in this high temperature space. So let's see, I'll go to the next one. Another question from Lawrence Russell. Your competitors dabble in additive techniques but only speak to its cost reducing capabilities, if at all. Is this because they aren't using laser powder bed fusion, or do they have a wider missed opportunity with the power of additive? So, I can't speak, too much about what our competitors are doing or how they, are introducing this technology. But for us, we view as being cost competitive has to be a base to any new, like that's core to any new technology insertion, but also, the higher performance that we get. That's, really the point of this webinar is, trying to get the idea out there that it's not about, the status quo of having the same type of material properties that have always been available. So really, when you match the alloy selection to the process, you get these added benefits as well. Let's see, question from Dana Godinez. What do you know so far about the fatigue life of C103? To date, we're seeing similar or better performance as well in high cycle fatigue of this material. It's highly ductile materials, and the microstructure is very amenable to high cycle fatigue life. So no concerns as of right now, especially considering we're playing a very dense material. Typically 99.97 or higher density. And so we don't see any void causing early initiation or failure either. We don't have any data out there in the public space, but if you have certain applications and want to talk about that, we can definitely share more offline. Another question from Lawrence Russell. A key in orbit technology as long as in the installation of additive manufacturing aboard space stations. Does ADDMAN have perspective on how they might participate in the realization of such systems? How far we can in orbit manufacturing supply chain? And this is our short answer live. So I would say, like ADDMAN, this isn't necessarily a high priority for us. We think it's still very low TRL, which kind of relegates it to be more aligned with maybe earlier stage companies, or in the university space, or R&D, kind of laboratory environment. I think it's really exciting, and we can certainly have a lot of materials expertise that we can lend here, but I would say it's not high priority on ADDMAN's kind of technology roadmap today. All right, and a question from George Westner. What is your current size limitation for producing C103 parts? So we printed full-size EOS M400 site parts, upwards of 383 diameter by, I believe it was 397 diameter by 383 millimeters tall. And we have opportunities to go even larger than that in the works. And so if you have a concern about the size, let us know, and we could talk more offline under NDA about how we're overcoming some of those limitations. Can you support, and another question from George, can you support DFD classified manufacturing? If so, to what level? George, hopefully you have our contact information. This is something that we would definitely like to chat about, but we would have to do it offline and under NDA. Thank you. And one last question from Lawrence. Could we ask what's next for ADDMAN, particularly in additive? What problems are you looking to solve in the next 5 years? Really great question. We're actively looking at alloy development space to go even beyond what is possible with C103 today. So we talked about Super C103. We have some really engaged customers that we're actively developing that with. And then also there's a whole other litany of alloys that have historically been made that we're investigating, but also looking at from a clean sheet type of design. And then finally, I would say other AM technology. So we think we have a lot of value to bear in the laser powder bed fusion arena. And we think that we have the right team and the right resources to go start tackling other technologies as well, and industrialize those. So great question. Really appreciate that. And I think that's all the questions. If you have any more, hopefully Hope can collect those. Feel free, or if you have my contact information, feel free to reach out. George, I think you had some specific things that we definitely would like to chat about afterwards, just probably not on this webinar. With that, I guess, Hope, did we have any other items we wanted to cover, or are we good for today?
No, thank you everyone for joining, and we will follow up. So thank you.
Thanks everyone so much. You have a great day.